Before getting right into the presentation, I'd like to just mention that Minitab actually published a new software last week. It's called Companion. If you go to our website, you will have here a Learn More button, and you will be able to learn a bit more about it. It will allow you to deal with all the non-statistical aspects of your process improvement projects, such as value stream mapping, 5S, etc., all the Lean and Six Sigma tools you currently use, and also to have a dashboard to see how all the projects in your company are going so far. So it's not today's subject, so I won't spend more time on that. Feel free to go to our website, ask me if you have any question, if you need any demo, and I'll try to include that in later presentations during the year. But now back to today's presentation. So as you all know, the presentations we are going to do today, we will stick to under half an hour, and we will discuss the importance of randomization of trials. So the randomization is an important subject, very specific to two tools that you have in Minitab. So the first tool is design of experiment, all of them, but design of experiment. And the second tool is in quality tools, gauge study or measurement system analysis. Today, we're going to have a look at a specific example from gauge study, but please keep in mind that if you do a DOE, everything we're going to say today is going to be true. So the first question is, what is randomization? So what I'll do is just create a DOE and then a measurement system analysis so that you can actually see what that is. First, we'll go for the DOE, and I'll do that through the assistant. So assistant, design of experiments, plan and create. And I'm going to create a screening design with a response called response. Number of factors 6. We'll name them A, B, C, D, E, F. A, B, C, D, E, F. And the first ones are continuous between 10 and 100, between 15 and 150, 20 and 200, 30 and 300, and the last ones, let's say, are categorical, and we have A and B and C and D. And yeah, someone told me I made a mistake here. It's 100. Thank you. So if I click OK, I have a total of 12 tests, 12 experiments, and I get this worksheet here with my 12 experiments. If I do that again, design of experiments, plan and create, I go to the same, use exactly the same configuration and click on OK. And now I'm going to put my two worksheets side by side, tile them. What you can see is that the order of the tests are different. So here I've got a worksheet with A 110, 110, and here I have 1010, 110. So the order of the trials is different. You see here that I have a standard order in both worksheets, and if I sort the worksheet by the standard order, I'll see that my 12 experiments are exactly the same for the first worksheet and the second one, but the order is different. If I go to Quality Tools Gauge Study, here I have the opportunity to create a gauge study, and you see that the effect is the same. So I have 10 parts, 3 operators, and I'm going to do 2 replicates, meaning that each operator is going to do the measurement twice. Click on OK, and I'll do that a second time. Gauge study, create a gauge study, OK. And if I put my 2 worksheets side by side, again, you'll see that I have the parts in different orders. So we have some randomization at the operator level because we have operator 1, then 2, and 3, and then we go back to 1, 2, and 3. We don't have 1 doing all the measurements, then 2, then 3. And inside each operator, we have the parts completely random. So I've got 259 here and 910 8 here. So that's what the randomization is. And column 1 is the run order. So that's the order in which I have to do my experiments. The presentation today will try to show you why this is important. And in order to do so, I have selected an example that we use in training to talk about measurement system analysis. So here we have a system where we measure the diameter of some nozzles, and the reference, the average is 9,012 microns. And we tried to see if our measurement system is good, and this is the base example that I'm going to transform in a minute. And the measurement system is very good in the base example. So if I go to stats, quality tools, gauge study, analyze cross gauge R&R study with nozzle, operator, and diameter, click on OK. And here I get a standard gauge R&R study. So just to quickly recap, if some of you are not that familiar with gauge R&R study, what we're trying to do is identify if the variation in the numbers we get in the end results comes from the difference between the parts, which would be good, or from the measurement system. So what we do is see if the parts, here the nozzles, are significant, the operators are a significant factor, and if the interactions between the two is significant or not. If the interaction is not significant, we then have another ANOVA with just the parts, the nozzles here, and the operators. And from there, we are able to work out this table here and the one under, and this table attributes the variation to one component or the other. And here we have 3 components, which are the 3 main components. We have the part-to-part variation, so meaning the variation between one part and the other, one nozzle and the other. And in a gauge R&R study, what I want is to have a lot of variation there, because that means that the variation in the numbers I see actually comes from the parts. So my measurement system is very precise. The reference level would be here 1% to have a very good measurement system. So under 1%, we definitely have a good measurement system. I'm not going into more details today. The variability of the measurement system is then decomposed into 2 main things, repeatability and reproducibility. Okay? And inside reproducibility is the operator, and if we have an interaction, then we would have here the nozzle operator interaction. So here we have a base that is actually very good. And what we're going to do is introduce an additional variation that's going to change that. And we will want to be able to actually identify it. So We have three main sources of variation. So the parts, the operators, which is actually the reproducibility, and the repeatability, meaning something else, not the operators and not the parts. I have prepared a table here with all the tests we are going to do. So the first four are going to present a defect, an order, an actual order, and the fifth one is going to be completely randomized in the necessary way. So we have here the parts, the operators, and something else. So what I've done is going back to the worksheet, I have added an offset to my measurements, and that offset changes. I'm going to present you with a graph of the offset. That's actually an offset that could happen. You'll see why. So when we start our trials, we set up all the material and we have a machine that warms up over time. And that machine gets more and more precise. It could be the opposite way, more and more imprecise, doesn't really matter. And what happens is we do the first half of all of our tests, then we go for a break, maybe we go for lunch. And when we come back, we have a significant difference, but it still continues to evolve. So it's a simple example, but that can happen. Typically, if you do a design of experiments, maybe you're not able to do all the experiments on one day or on 1 week, and you have to do the other half at a different time. For this case, let's just say that we go for a lunch break, and when we come back, the conditions are a little different. So what I will want in my analysis is to see that this variation introduced here doesn't come from the parts. It doesn't come from the parts I'm measuring. It doesn't come from the operators. Okay, it actually comes from something else that I have to identify. So we're going to do 5 experiments, and the first one here, what I have done is change the order so that we have an operator order. So I've got the first operator doing all his measurements, and then a second operator doing all his measurements. The order of the nozzles of the parts is still completely random, but not the operators. So I'll go to Stat, Control Tools, Gauge Study, Crusts, and here I'm going to go for the final result, which is actually the diameter, the original one, plus the offset. Okay, so that changes my result. Click on OK, and I get this result, and for the rest of the presentation, I'll go directly to the percentage composition without having a look at the rest, because that's what I'm really interested in today. So here I have the decomposition of variation, and this first analysis attributes 97% and a half to the measurement system, which is good. That's where the variation comes from in my case, but it attributes it to the operators mainly, and it gives only 2.5% to the part-to-part variation. So here, really, what I have is not what I would want. What I want is to see the main variation here, something else. And what I get here is 2.5% for part-to-part. I'll round my numbers. Operators would be 96%. Let's say 96%. And the rest, which would be 1.5 rounding the numbers, is something else. So here would be my main source of variation, and that is not true. So not what I would want if the study was good. Because here what's going to happen is I'm going to say, okay, the problem is between the operators, so I'll work on factors that can be the source of that variation, but I'm not looking at the real thing. I'm not looking at the source of my variation. So we'll have a look at a second configuration, which is measuring the parts in order. So I get a first part and I don't want to move it, so I ask both operators to do their measurements. Then I get a second part and I ask another operator to do his measurements. If the parts I'm producing are heavy or take a lot of space, that could be a tendency that we would have. So I bring the first piece, the first part, and ask operator 1 to measure it, then operator 2, and 1 and 2 again. I'll go to Stats, Quality Tools, Gauge Study, and the analysis is just the same as before. Click on OK. Go to the results. And here I can see that 92.2% is 0.3% is attributed to the part-to-part variation. So the parts would be 92.3%, and my measurement system takes 7.7%. And this 7.7% is attributed to the repeatability, not the reproducibility, so not the operators. So here the operators are safe, which is actually what it is, right? The operators don't have anything to do with it. I still identifies that my measurement system is not good enough. Okay, it's not the 1% I would be looking for, but the magnitude of my conclusion is not good, not good at all. So that wouldn't be good. And here the main source of variation still is the parts, which is not true. The next worksheet we're going to work with is also some kind of part order. So instead of ordering by part number, what we've done is we've ordered it by size. So if I'm measuring a distance, if I have steel bars, for example, and I measure them, what we could have a tendency to do is first bring the smallest one and then progress to go to the biggest one. Or if we have heavy parts, start with the lighter one and then move on to heavier and heavier. So we have some kind of logical order here. And we see that if we do the analysis again, okay, we'll get a different result. So it's important to understand that the result is going to differ depending on the order of the parts. And here what we have is we still attribute the main variation to the part-to-part differences. So 87.5 for the parts, 87.5, and the rest is attributed to the repeatability, so 12.5. And the operators are still safe. We still see that our measurement system is not good, but the identification of the problem would still be here, and that's not really what we would want. Okay, the magnitude is not the right one. Fourth example, fourth case of mistake, we'll go to an order for both the operators and the nozzle. So that would be a bad case. Was going to say maybe the worst, but really all the results are misleading in our cases. And what we do is we get operator 1 and he's going to do all his measurements, and he starts with part one. So part one, first time, second time, part two, first time, second time, and so on and so forth, until we get to part 9 for operator 2. I'll do the same analysis as usual, and now when I get to my results, I can see that very little is attributed to the part-to-part variation, only 4%, 4.1%. The rest to the measurement system, but only to the operators. So I get 95.8% for the operators, and they have really nothing to do with that, and 4% for the parts. So 4.1 here, the parts 4.1, the operators 95.8, 98, and the rest, so only if I round the numbers 0.1 would go to something else, and that's not really what I want. So now what we're going to do is we're going to go to the last example where we actually do what we need to do, which is respect the randomization of the test. So what I've done is go back to the base worksheet, the same order as the base example, but with that difference that we should have here, so difference in measurement. I go to Stat, Quality Tools, Gauge Study, and here Cross, and click on OK. And now what I'm going to see in my results is that 100% of the variation is going to be attributed to repeatability. So the operators don't have anything to do with that. The parts don't have anything to do with what I'm able to see. So I have 0 for the parts and 0 for the operators. And 100% is attributed to something else in my case. So here I rightly detect that the problem doesn't come from the parts. Having a lot of variation from the parts would be a good thing. The problem doesn't come from the operators. They have nothing to do with it, and if they actually measure in the same way. Here really it comes from something else. So the only case in which I managed to identify the issue, the source of the issue, is with a fully well done randomized test. And that's going to be the same for designing of experiments again. So I hope I got the point across today. That's the end of the presentation I had, and I can stay a little bit longer if you have any questions. I'm going